and I work in Aarhus in Denmark, and I'm working on Google Chrome. And in particular, I'm working on the JavaScript engine used in Google Chrome called V8. And that's what I'm going to mainly talk to you about today. So I'm going to tell you a little bit about Google Chrome, so why Google decided to build Google Chrome. I'm going to try to kind of go through that quickly, because you probably all went to the keynote where some of this was already mentioned. And then I'm going to tell you why we wanted to design a new virtual machine for JavaScript. And I'm going to tell you some of the details of its implementation, so what we've done to try to make JavaScript execution really fast. Okay, so let's start by talking a bit about Google Chrome. So the internet has evolved a lot over the last 10 years. So to try to illustrate that, here's a slide on the evolution of the internet. So it shows the BBC web page from July 1998 to August 2008. And basically what you can see here is that web pages have gone from being mainly text-based to being these highly interactive things where you've got videos, you've got pictures, and you've got all kinds of interactive content. And users spend more and more of their time inside of their browsers. So at Google, we spend a lot of our time inside of our browsers. We've got our email clients, our calendars, our collaborative documents, a lot of stuff inside of our browsers. And these are full-featured applications. I mean, it's not just like simple web pages. They're really full-featured applications, a full email client, a full calendar program, and stuff like that. And all of this is inside of our browser in different tabs. So really, the internet has evolved a lot, and we use our browsers in a completely different way than we used to. But basically, the underlying browser architecture has not evolved that much. It has evolved much more slowly. We have seen development, right? I mean, we do have tabs now, which is really great. But still, evolution is really, really slow in the browser market. So that's what so that's why we wanted to introduce Google Chrome. We wanted to try to push evolution of browsers in general. We wanted to try out, try to change the basic architecture of the browser to give you better stability. We wanted to try to build a very intuitive browser that's easy to use, and we wanted to build a fast browser. So if we take each of these in turn, Google Chrome uses a multiprocess architecture. So as I showed you in the keynote with the demo, if one tab goes bad in Google Chrome, only that tab is affected. If a plugin goes bad, only the content that needs the plugin goes bad. Nothing else is affected. You can go to your other tabs and you can continue browsing. Also, we try to make Google Chrome very easy to use. So in general, Google Chrome tries to get out of your way. Basically, we wanted to kind of design an invisible browser. We don't want users to worry about their browsers. What's really important is the content. We want people to interact with our web pages and not so much with the browser itself. So Google Chrome tries to get out of your way as much as possible, so it doesn't take up very much space on the screen and stuff like that. Also, Google Chrome has very flexible tab management. So you can move your tabs around anywhere you like. You can even drag out tabs from one window and create a new window, and you can drag tabs between windows. Also, Google Chrome has a combined search and address bar called the Omnibox, which gives you suggestions as you type, and it has really nice search features too. So with this new Omnibox, we try to make it really quick for you to go to where you want to go to find what you need to find. And the final point is that we wanted Google Chrome to be really fast. So why does fast browsers matter? Well, it matters because the faster your browser is, the better web applications you can create for these browsers. So we wanted to make Google Chrome really fast, and we did two things to make Google Chrome fast. The first thing we did was to base it on WebKit, which is a really fast rendering engine. And the second thing that we did was to implement a completely new JavaScript engine from scratch and integrate that into WebKit and use that in Google Chrome. And that's what I'm going to tell you about now, V8, the JavaScript engine. So why did we want to build a new JavaScript engine? Well, we started this project 2 years ago, and at that point, the JavaScript picture was not really looking that good. Browsers had really slow JavaScript implementations. And the JavaScript engines didn't really scale with respect to code size and object allocations and stuff like that. And some of them even had like memory leaks when running your web applications. So we wanted to try and see if we could do something about that. And we wanted to do that by building a completely new JavaScript engine where we'd try to avoid some of these pitfalls. So we started the V8 project. And the goal of V8 was to raise the performance bar of JavaScript execution. So we wanted to show that JavaScript execution can be really fast. And we wanted to try to kind of push evolution here. So there are a number of key design ideas that we use to make V8 really fast. And I've listed 3 of them here. So the first one is something called hidden classes and hidden class transitions. So JavaScript is a dynamic object-oriented language. There are no classes or anything like that. So the standard object-oriented class-based optimizations, you can't really use them on JavaScript because you don't have a notion of class. So we wanted to use these optimization techniques. So behind the scenes, we basically introduce classes for you. So inside of the engine, we have a concept of a class, and we can use class-based optimization techniques such as inline caching to make JavaScript really fast. So the second thing that we do is that we compile to native code. And the third thing that we do is that we have an efficient memory management system. And by that I mean that if you write a big application that creates a lot of objects, if you do not design your memory management system to take this into account, you'll experience big pause times. And that's going to be quite annoying when you use your browser if something lags because JavaScript needs to garbage collect its heap. So we've designed an efficient memory management system and used an efficient memory management system to get small garbage collection pause times, so you won't really notice it when you're browsing. Okay, and I'll try to go into each of these now. So I'll start out by the hidden classes. So let's first look at some of the challenges of implementing JavaScript. So JavaScript is this really dynamic programming language. So objects are just mappings from property names to the values. And you can add properties to objects whenever you want to. You can delete properties from objects. Properties can be found in the prototype chain of objects. So JavaScript has this, basically uses a prototype chain for its inheritance. So what this means is that if you have an access site in your code, so you have an object O and you want to get its X property, so O.X, you don't know what O is. You have no idea because a lot of different objects could flow into this access site. And they could have completely different layouts. They could have completely different sets of properties. So basically, you don't know where anything is. And that makes it a bit hard to do efficient lookup. Right, so let's look at that some more. So if you have like a static class-based object-oriented language, then for every object, you know its class, and based on its class, you know the layout of the object. You know where fields are, you know where methods are, you know like the offset inside of the object. And that means, and also you know statically at a given point in the code, which class your object is going to have. So you know you're only going to see objects with that class at this point. So you can do a direct load from the object, and that's really, really fast. All you have to do is kind of go to a certain index in your object and just directly load a value, and that's really fast. So in JavaScript, we don't have any classes, and it's really dynamic, and you can change your objects any way you like, and you don't know anything at an access site about your object. So that means that basically, when you want to load property X from an object, you basically have to search the object for it. You have to look at the object itself. If you don't find it there, you have to go to the prototype. Look for it there. If you don't find it there, you have to continue up the prototype chain. And that's really slow. So basically, we wanted to move away from this search approach, where we kind of search through everything, which is really slow, and move towards what you would do for a static class-based language. And in order to do that, we introduce kind of classes behind the scenes. So the users don't see them, they're not in the language, but in the implementation, we have a notion of a class. So we call it a hidden class. So here's an example. All objects in JavaScript are created based on functions. So here's a point function for creating point objects. And all it does is it creates a point object and assigns an X and a Y value to the X and Y properties of the object. Okay, so let me try to show you how these two objects, P and Q, that I created at the bottom, how they're going to end up having the same hidden class inside of V8. So when I execute new point, I'm going to create a new point at the top here, and it has some backing storage for holding properties. It has some space for putting in values of properties. And every object that's created from the class, from the function point, will start out having this class C0. So the class C0 is associated with the function. So whenever you say new point, that new object is going to have the class C0. Okay, so now I've created my object. It has an initial class. So now I'll start executing the function, the code inside of the function. So first I'm going to add the X property to my object. And what I'm going to do to add the X property is to take the value of the X property, which is 1, put it in the backing storage. Okay? Then I'm going to change the class of my point to record that X is at offset 0 in my backing storage. So I'm going to take a copy of the class C0 and add to it that X is at offset 0. And then in the class C0, I'm going to record that if you have an object that has this class and you want to add an X property, your object needs to get class 1. Okay? So we have classes and we have transitions between them. Okay, so when we do the same for Y, it's going to look exactly the same. We're going to take the 2, we're going to put it in the backing storage. We're going to record in class C1 that if you add a Y property, you need to transition to this new class C2, which has X at offset 0 and Y at offset 1. Okay, so now I've finished the creation of my first point, and it ends up having class C2. So now let's go quickly through the creation of the point Q. So again, when I do new point, I'm going to create a point object. It has a backing storage, and it's going to have the class C0 because the class C0 is associated with the point function. So everything I create based on point will have that class C0. And now I'll go through exactly the same steps as I did for the other point, right? The only difference here is that I don't have to create any new classes because they're already there. So when I want to add an X property, I look at my class C0, and I can see that the class C0 says that if I add an X property, my object needs to get class C1. So all I have to do is update the class pointer and put the value in the backing storage, like that. And the same for the Y. So now these two objects have been created, and they end up having the same class C2. So you can see for the first point that I create, there's going to be a bit of overhead here, because I have these classes, and I copy and extend them, and put in map transitions, or class transitions. There's going to be a bit of overhead the first time, but after that, it's going to be just simple pointer updates. Okay, so now doing this thing with hidden classes and the transitions between them so that you kind of change class when your object dynamically changes, we have a notion of a class inside of V8. I mean, all objects have a class that kind of describes the layout of the object. So using this, we can kind of revisit my statement from before. I said that JavaScript is this really, really, really dynamic language, and it's really hard to figure out what's going on. So is that really the case? And it turns out that it's not really the case. So if you instrument your code and look at the hidden classes that you'll see at different access sites, you'll see that in roughly 90% of all access sites, you will only see objects that have one hidden class. You'll only see one hidden class at that access point. And that kind of makes sense, because if you write like well-structured, object-oriented programs, you're probably going to write it in a way that certain parts of your code are going to be concerned with a specific kind of object. So basically, it makes sense that a lot of your code will only see an object that has a certain form. And that's definitely what you do when you write like well-structured, object-oriented programs that are easy to understand. So roughly 90% of all access sites only see objects with the same hidden class. And the conclusion of that is that JavaScript is really not that dynamic. And we can actually use some of the class-based object-oriented optimization techniques. And in particular, we can use something called inline caching. So in inline caching, each property access is controlled by a little piece of code called an inline cache stub. And these inline cache stubs can be in one of 4 different states. So the first state is uninitialized, and that's the state every inline cache will start in. And that just means that I haven't seen anything yet, so I don't know. So I haven't seen any hidden classes yet, so I don't know anything. Okay. So then when you see the first hidden class, you're going to move to a next state, which is called pre-monomorphic. That's not really that interesting. It just says, I have seen one hidden class, but I'm not really ready to commit to anything yet. The third one is the one that's really interesting. And that is, when you see the second hidden class, you're going to say, okay, so I've seen a hidden class here. I've seen one hidden class. And I'm going to assume that the next time I get here, I'll see the same hidden class. So I'm going to, on the fly, create a little piece of assembly code, and I'm going to use that for my property access. And that assembly code is going to have the assumption that the next time I get an object here, it's going to have the same hidden class as the object I'm seeing right now. So that assembly code has to do only a few things. It has to check that we're really looking at an object. It has to check that that object actually has the hidden class that we expect. If it does, it can do a direct load from an offset in the backing storage, which is what the class-based, static class-based object-oriented languages are able to do too. So this is really fast. So the third case there, the monomorphic case, is really, really fast. It's like 10 lines of assembly code. So if one of these assumptions are invalidated, if somehow a basic thing comes in there, like a number or a string or something, that's not an object, we're going to bail out and go to the fourth state, which is megamorphic. Or if we see more different hidden classes, so our assumptions basically break. We're not only seeing one hidden class here. We're going to bail out, and we're going to use what's called a megamorphic inline stub instead, which can take care of more different hidden classes, but it's slower than the third case. So remember that 90% of our access sites will end up in the monomorphic one, because 90% of our access sites will only see one hidden class, and I'll end up with the fast case. So the fast case really is fast. So here's the actual assembly code generated for an access. This is x86 assembler. So let me try to walk you through it. So the first line just says, get the receiver into EAX from the stack. Okay. So the next thing we need to do is to check that we actually have an object. And this is a bit technical, but all pointers in V8 are tagged. So, and that's basically to be able to recognize if you have an integer or you have a pointer to an object. So the next two lines are just checking, do I have an object or do I have an integer? Okay. If I have an object, I'm going to take the object, read out its hidden class, and compare it against a constant, which is the hidden class that I expect. Okay. So if that's all fine, I'll go down here and I'll load the backing storage, and I'll load the value at a fixed offset, which I know from this hidden class, and then I'm done. Okay, so a lot of accesses will go through this, just a few assembly instructions, and it's really fast. And if any of the assumption breaks, if I actually get in an integer here, I'm going to jump. Or if my hidden class does not match what I expect it to, I'll jump out here and go to an inline cache miss stub, which is going to rewrite the code to use a megamorphic stub, the one that's used when you've seen more than one hidden class. But a lot of your property accesses will look like this, and that's one of the big things that makes V8 really fast. Another thing we decided to do was to do native code compilation. So we do not have any bytecode format or anything like that. We do not have an interpreter. So all of our code is compiled to native code. And that doesn't mean that when we see some JavaScript code, we immediately compile everything to assembly code. So basically, we just record that if there's a function, we just say, okay, here's a function. It has this source code. And then the first time we try to execute that function, we know that we have to compile it. So we do this JIT-style function compilation, so lazy compilation of functions. So when we want to use a function, what we're going to do is do a very simple compilation. So we're going to pass the source code into an abstract syntax tree, and then we're going to do a very simple one-pass code generation. Just going to spit out the code in one pass, and we have very few optimizations currently in our compiler. So it's pretty simple. And we have compilers, code generators for x86 and for R. Okay. On to efficient memory management. So we had a couple of design goals for the V8 memory management. We wanted object allocation to be really fast. If you write object-oriented programs, you're going to have a lot of object allocations, and we want that to be really fast. So we're aiming for having object allocations that are just bumping a pointer. So just a single pointer increment. We want to have a scalable object heap where we had small garbage collection pauses. And the way we do that is that we use a generational garbage collector. And I'll tell you some more about that right now. So here's the organization of our heap. So we have two generations. We have a young generation and we have an old generation. And we have these two generations to make sure that we have small garbage collection pauses. So the young generation is garbage collected frequently, and the old generation, we only garbage collect rarely. Okay? So that means that everything that's in the old generation, we don't look at garbage collections that often. Okay? So in the young generation, that's where we put all of our newly allocated objects. And the idea here is that when you allocate a new object, it's probably going to die pretty soon. So that's like a characteristic of object-oriented programming, that you have like a lot of temporary objects. So basically, objects die young. So we put all newly allocated objects in young space, in the young generation, in new space, and we garbage collect that frequently. And most of the time, a lot of the space there is going to be freed up because objects die young, so we allocate them there, and then we remove all the ones that are not used, allocate, remove all the ones that are not used. Okay, so that's, most of the time that's enough. But sometimes we do have to garbage collect everything. And then we have to look at the old generation too. So the old generation is where objects move when they've survived a couple of garbage collections in the young generation. And the idea there is that if your object survives a couple of times in the young generation, it's probably going to survive a number of extra times. So we don't really want to look at it at each garbage collection because it's probably going to be alive, so we're probably going to have to keep it. Okay, so we move it to the old generation and say, I don't want to worry about this object because it's probably going to be alive. And then we continue garbage collection thing, the young generation. So only occasionally we go to garbage collect the old generation. And the old generation has a number of spaces. I'm not going to go into all of them. I'm just going to highlight a couple. So we have like a code space. So I told you about these inline cache stubs. And that's assembly code that we generate on the fly. All this assembly code is put into code objects that we put into the heap. And it's garbage collected like every other object. Okay, so we put that into code space. And we have, and the reason why we have a code space is that for code, we need to use executable memory. Okay, so we put all of that in the code space. And then there are a couple of other spaces, and we have a space called large object space. So if you have very big objects that are larger than 8 kilobytes, we don't really want to move them around. So we put them in large object space, and they stay there. Okay, so we don't waste time moving very, very big objects around the heap. Okay. So we use a couple of different types of garbage collection. So for the young generation, and that's what happens frequently, we use a copying collector. A copying collector allows you to do single pointer allocation. Because when you're done garbage collecting, all of your data will be compactly at the beginning of your space. So all you have to do is bump a pointer to get some extra space. And the pause times for a copying collector is bound by the amount of live data in your young generation. And since most objects die young, there's not going to be much live data in the young generation. So that means that we get typical pause times of 1 to 2 milliseconds. And that's not something you're going to notice at all. So when we do full garbage collections, where we have to look at both the young and the old generation, we use a mark sweep collection. And that processes all of your spaces. And the way we've implemented this, it allows us to use a combination of single pointer allocation, again just bumping a pointer, and tree list allocation. So it's one or the other depending on whether you could do the single pointer allocation or not. And the pause times for a mock sweep collection is bound by the size of the heap. Okay, so that's a different story than for the copy and collector. And that gives us typical pause times for big web applications of 30 to 50 milliseconds. And then once in a while, if there's too much fragmentation in the heap, so we keep track of how much fragmentation we have in our heap, and if it reaches a certain threshold, we're going to do a mock sweep compact collection to eliminate fragmentation. And for that, you'll get typical pause times of like 50 to 150 milliseconds. And that's where it becomes, that's a bit much. We'd like to get that lower. Right, and this is only for like really big applications. For small applications, the mock sweep and the mock sweep compact times will be smaller than this. But for big applications, you'll get pause times of up to 150 milliseconds. Okay, so here's another interesting thing we do in V8. So JavaScript has a number of library functions, like string.prototype.split or array.prototype.join, and so on. There are a lot of like built-in functions and strings and arrays and numbers and stuff like that. And all of these library functions in V8 are implemented in JavaScript. So we do not have any of this code in C++ inside the JavaScript engine itself, but we write it in JavaScript, and then we compile the JavaScript using our own compiler, and then we execute that whenever the user wants to use one of these library functions. So what are the benefits of implementing the basic libraries inside of JavaScript instead of inside of the engine itself? Well, one of the big ones is that it keeps the core JavaScript engine much cleaner. There's less code in there. Also, it's really easy to change our libraries. We just have to change the JavaScript code, and our compiler will take care of that. And we don't have to basically rebuild V8 in order to do that. Also, there's another really cool thing. So since this JavaScript code that we have for the libraries, that's handled by our own compiler. So if we improve our compiler, not only are we going to make like user code run faster, we're also going to make the library functions run faster. So if we improve our compiler, we're going to improve our library as well. Okay, so there's one drawback to doing this. And the drawback is exactly that we have to compile this JavaScript code. So at startup, we basically need to load a number of files and compile the source code into native code that's put in our heap, and then we can start executing. And that gives us a startup time of roughly 30 milliseconds, and that's quite a lot. But there's a solution to that. So V8 allows you to basically save a binary snapshot of the initial heap. So what we do is we have one version of V8 that loads the JavaScript files, compile them to native code, puts it in the heap, and then it dumps the heap in a binary format. And then that binary format of the heap is going to be integrated in another version of V8, which at startup time is not going to load any JavaScript files. It's not going to compile any JavaScript code. It's just going to load the binary image that's a part of the actual V8 executable into the heap and then start executing. And that gives a startup time of 4 to 8 milliseconds, which is acceptable. Okay, so basically snapshotting allows us to do this. I mean, it allows us to write our library functions in JavaScript and still get reasonable startup times. Right, so with V8, we also published a number of benchmark programs. These are programs that were already out there. They're not written by us, they're written by other people. And they're like object-oriented programs, well-factored programs. It's the kind of programs that I think represents what big web apps are doing. And there's like 11,000 lines of code out there. And you should have a look at them if you want to. Right, and here's a really important thing. V8 is fully open source. So all of the source code for V8 is available at code.google.com/p/v8. And all of our development takes place there too. So you can see all of the things that we're doing. You can see our code reviews, you can see our mistakes, you can see everything. And the reason for this is, of course, that we want to push, and Chrome is fully open source too at chromium.org. So we really want to push the development of browsers in general. This is not just like for Google Chrome. We really want browsers to get better in general. We want to have faster browsers in general so that web developers can actually do more on the web. Right, I think that's all for me. So I'll be happy to take any questions you have.